Good afternoon, everyone. My name is Marek Isala, Senior Coordinator for Advocacy at SEMI Europe, and it's my great pleasure to welcome you all to today's webinar. Now, as many of you know, a robust European semiconductor industry is of vital importance to the region's economic growth, resilience, and competitiveness globally. And while many of our great industry champions already heavily invest into research and development of critical innovations, some of the technological challenges that we face cannot be simply addressed by one single organization alone. And in this regard, European funding and EU-funded projects have played a critical role by connecting like-minded industry partners, academia, and RTOs to deliver collectively breakthrough innovations that can shape and advance our region's semiconductor industry in decades to come. So in today's webinar, we will take a look at some of the funding opportunities, not only for the semiconductor industry, but also at some critical innovations that can help your businesses to stay ahead of global competition. And now, please allow me to give the floor to our first speaker of today, Caroline Bedran, Director General of the Industry Association, INEAS.
Good afternoon. It is a pleasure for me to be here with you and introduce the research, development and innovation funding landscape, the impact of collaborative innovation, highlighting key digital technologies, and the Eureka XCCS cluster, and INEAS' role and support. Let me start with a few words about INEAS. INEAS is a not-for-profit association gathering more than 450 members. Those are all types: large companies, SMEs, research and technology organizations, and universities, all having research, development, and innovation activities. And you see on this slide the logo of our 20 board members: ST, NXP, Infineon, Thales, Airbus, Volkswagen, Philips, etc., covering the full value chain of electronic components and systems. Our president rotates every 3 years. Kurt Sievers from NXP is currently our president, and our board members are at the highest level in their organization, namely CTO or CEO level. INEAS' mission is to prepare the future landscape of funding instruments and help its members take benefit from those funding instruments. The ultimate goal is to support the sustainable digital transformation of Europe and make it more resilient in the future, delivering impact at economic and societal levels. Now, let us see a little more details about what INEAS does, starting with the vision, mission, and strategy. As just mentioned, our vision is a strong and prosperous Europe, a vision shared by our industry at large, by other industry associations, but also by European institutions and national governments. This is possible with advocacy actions and intimacy with the European Commission and national public authorities, participating with them in the governance of the funding instruments, such as the Key Digital Technologies GU Governing Board and Eureka clusters. But we also provide guidance, namely with the Strategic Research and Innovation Agenda, which is prepared by experts from our community and serve as the basis of the calls of those funding programs. Then we move to more operational tasks. INEAS in particular fully operates the Eureka clusters Penta, Euripides, which ended in 2021, as well as the new XCCS cluster, which is in its first call. INEAS participates directly in a few projects, mostly CSAs, coordination and support actions, preparing the future landscape of collaborative innovation in Europe, delivering roadmaps or analyzing challenges, gaps, and needs. And we also stimulate our members through many events, workshops, both to get their feedback, for instance, on the Strategic Research and Innovation Agenda, but also to inform them about the calls and stimulate their appetite to prepare proposals for collaborative projects. This slide depicts the European funding landscape for the ECS industry and you recognize the different elements. On the left, you see the pure national programs. On the right, the pure Commission programs under Horizon Europe. And in the middle, you find the two pillars in which INEAS is most active. Those two pillars are, on one hand, the Eureka clusters, which consist into transnational collaborative projects funded by each country member of the Eureka network. As said earlier, INEAS is involved in those clusters mostly suited to electronic components and systems, namely Penta, Euripides, and XCCS. On the other hand, the Key Digital Technology Joint Undertaking, which is a partnership under Horizon Europe, receiving support from the European Commission and participating states. I will explain a little more. First, Eureka clusters. Eureka was launched in 1985, and it is the world's biggest public network with more than 45 member countries supporting international cooperation in research, development, and innovation. The clusters are a joint initiative between public authorities and private organizations, again large and small companies, RTOs, and universities, dedicated to specific domains, and 5 clusters operate under Eureka: Celtic Next for telecommunication, Eurogia for energy, ITEC for software, SPART for manufacturing, and XCCS for electronic components and systems. The program of Eureka clusters was reviewed 2 years ago with the aim to strengthen it. It is open to all. It is agile, flexible, easy to use. Clusters are working both independently and together around joint cluster calls. And to give you a flavor of the size and the impact of a cluster, here are a few figures of Penta achievements over the past 6 years. There were 6 calls, 34 projects, 406 beneficiaries, 24 countries involved, for a total investment, public-private, of 385 million euro. Now let us move to KDT, Key Digital Technologies. It is a much bigger program compared to Eureka clusters. Projects are much bigger, also compared to projects under the regular Commission framework of Horizon Europe. This size justifies the need of a co-funded partnership to address the ambition of Europe in the coming decade. The budget of Key Digital Technologies is even bigger than Excel, which was under Horizon 2020. We moved from 4.8 billion euro to more than 7 billion euro for KDT over 7 years. KDT always covers electronic components and systems with an enlarged scope. Now, you also heard recently the Commission proposal of the EU Chips Act. The KDT joint undertaking should evolve into the Chips joint undertaking under the Chips Act, probably in the course of 2023. In KDT, INEAS, EPOS and Inside, which together represent the private members of the joint undertaking, the industry performing research and development activities, committed together on behalf of their industry members to mainly 2 points. Contribute in kind, which is the research, development and innovation activities, to more than 2.5 billion euro. This is net of grants. The second thing is to contribute in cash up to 26 million euro to the joint undertaking administrative cost, meaning the financing of the GU office in Brussels, which operates the KDT program. This picture illustrates how the joint undertaking works. It is governed by a governing board, in which industry, represented by the associations, has 1/3 of the votes, Commission 1/3, and participating states 1/3, which means that industry has a strong voice in the strategy and operations of the joint undertaking. It is governed by the rules of Horizon Europe, as well as the national rules for each beneficiary in its own country. Of course, the projects are meant to deliver impact. And in terms of impact, you are going to have presentations of 2 projects which were funded under Excel, the predecessor of key digital technologies. Therefore, let me first give you the big lines of Excel globally over the 7 years period it ran under Horizon 2020, from 2014 to 2020. As you can see in this slide, Excel delivered 96 projects, 3,220 beneficiaries, a total investment of 4.8 billion euros, including 2.3 billion euro in funding from the European Union and participating states. On average, 5,000 persons full-time equivalent were involved each year in Excel projects from 38 countries. And to know more, you can refer to the booklet of testimonials of top executives of our members, which can be downloaded with the link on this page. Now it is time to hand over to the 2 projects Made in 4 and IMOCO4.E, both running under Excel. But before doing so, let me remind you that Aeneas Association is here to help you, guide you through those funding instruments, advise you, help you network and find partners for your projects. Whether you need to manage fierce competition or cut innovation costs, funded collaborative projects help you tackle complex technological challenges, address research opportunities with partners having complementary skills along the value chain, and speed up your time to market. Thank you for your attention.
Hello, my name is Andres Torres. I'm a distinguished engineer at Siemens CDA, and today I want to present work in collaboration with Global Foundries entitled Virtual Cross Metrology, Leveraging Process Sequence for Improved Process Characterization. The agenda today is going to be an introduction, the difference between virtual metrology and virtual cross metrology, how we can use this information to interpret the results, and conclusions on future work. Individual process steps virtual metrology means that we have a process step that involves process tools and metrology. And it goes from the previous process step to the next process step. All of this historical data can be encapsulated into a virtual metrology system that it can predict the wafer outcome. The goal of virtual metrology is to provide more coverage at a lower cost. Every physical measurement that is taken, it's expensive, and the idea of virtual metrology is to increase the number of sample points that can be analyzed in order to have improved process monitoring, improved fault detection, or better process control. A overall process virtual metrology, so not only for one individual step, but for a concatenation of different processes, involved collecting all of that data, all of the process data, feed that into the virtual metrology system, use information about wafer acceptance tests that can be used in order to consider an acceptance criterion and also consider inter-process steps. Virtual cross metrology is the idea that in addition to the process information, as was stated before, every process step has metrology that is used for inline characterization of the system. The idea of virtual cross metrology is that not only the process information it's used to feed into the virtual metrology system, but also all of the signals that are related to the metrology data can be also incorporated into the metrology system. This allows a prediction of the wafer outcome at any position on the point in the process, and also incorporating the product information. And we will see why the product information is necessary. The goal of this approach is to improve accuracy and also improve interpretability. Interpretability is important from the point of view of identifying which are the locations in the process where the biggest payback of making a change would result. How can we learn from other designs? The idea is that we are going to extract design information, so from different designs here as indicated as rows, design 1, design 2, design 3, design 4, each one of these different views of the design can be extracted, and this is parameter or component 1, 2, 3, 4, 5, all the way to 7, that provides different design features that allows us to look at the relationship that exists between those design features and their response to a specific process and metrology steps. The idea is that by combining all of these different parameters, we are able to generate a process model that is able to tell us what is the relative importance of each one of the different metrology, process, or design parameters into the system. What we want to do is to learn from other metrology measurements. As explained before, one of the things that we want to do is to have full coverage over all of the different metrology measurements that we are going to collect. Today, that is impossible because it's very expensive, and therefore we need to have basically this incomplete representation of the manufacturing of our devices, which makes it very, very difficult to align the behavior of the different process steps. The idea of cross metrology is to fill in the gaps of every single measurement, of every kind of measurement across the full stack of the design, so that we can actually identify what are the relative contributions that each individual process step provides to the final result. From the point of view of virtual cross metrology, we are actually going to compare two different scenarios in order to have a better idea of what is the level of interpretability that we can get with these different results. We are going to have an intra approach and an inter approach. The intra approach basically means that only the information of the metrology parameters that were extracted in that particular process step are the ones that are being used. However, the full history of the process information, it's also carried around. What we can also do is not only carry the information from the process, but also the information about all of the different metrology steps. Different measurements are taken in different locations. So in order to carry that information, there have to be models that get generated so that they are able to complete the full stack over all of the different process parameters that have occurred before the final measurement. That's really going to be the difference between inter and intra. In both cases, they are going to contain all of the process information, but only in the inter approach is where information of previous metrology steps from previous process steps are going to be incorporated in order to achieve a better result of the final metrology tool. This is an example of how we are going to present the data between the model calibration and normalizing, or model training and normalizing to the process range. We have in these pictures going to have a calibration set, we're going to have a test set, and we're going to have a combination of the two. When we have in the y-axis is the target experimental result versus the simulated. We are going to use 80% of the data for training, 20% of the data for validation and test. The results that we are going to report are going to be the root mean square error, the mean absolute error, as percentages of the process range. The process range is the full range of the observed target during the accumulated operation conditions. That's what we take into account in order to only consider not a predetermined range, but a range that it was observed during operation. This is a table that shows intra versus inter virtual cross metrology results. We are going to have different process steps. So we are going to have a process sequence, in this case, composed of 3 different process steps. Process step 1 has 4 different measurements or 4 different characteristics that are used to characterize that particular process step. There are 5 characteristics or 5 attributes, measurements, that are used to characterize process 2, and also 5 labels that are used to describe process 3. And as you can see here, for both calibration and test, we have the intra and the inter VCM results. As expected, so we are, instead of showing the details of all of these different experiments, what we are going to do is we are going to select 3 different conditions. The first condition is basically the first one. The first one in which we should get very, very similar results because there are no previous processes. It's only using the measurements in that particular process step. So that's why you can see that for the training and for the test of the intra VCM, it's 1.17, 1.3, root mean square 4.33, root mean square 4.0, maximum absolute error 3.2, 3.2. So this gives us an idea that these models are basically equivalent between each other because at the end of the day, they are modeling exactly the same thing. Why are they different at all? They are different because, remember, machine learning is reliant on a certain level of randomness in which the way that the model and the product has been created. So after repeating this process several times, what we can do is make a comparison, and this gives us an idea of the level of repeatability that we get between different models. So what this is basically telling us is that from the point of view of root mean square, there may be an up to 0.3% difference in the observed values that we have. So anything that is greater than that starts to become significant. We go to another example in which we can go and say, okay, this is a particular case in which the maximum absolute error in the test set is 1.03 versus 1.23. This is one of the cases in which the intra-VCM approach seems to have a better accuracy than the inter-VCM approach. But again, notice the differences that we were talking about. We are basically saying that about 0.1% differences really are subjected to difference in the model. So this is basically what we have in this particular case. We have a difference of around 0.2 difference, but nevertheless, it's a case in which intra-VCM, it seems to be providing a better accuracy than inter-VCM. And then we have another example which shows the largest difference, that an intra-VCM approach has a maximum absolute error, mean absolute error of 5.75 versus 5.06. So we are going to explore in detail the difference of these two cases, and this is going to be the very first lesson that we are going to obtain from all of this, that if we are only looking from the point of view of accuracy, of how well we are able to match the expected error, there are multiple approaches that actually allow to have a very, very small error. As you can see here, in all of these cases, there is nothing that has an error greater than 10%. Everything is under 6%. From that point of view, will be, well, why are we actually even doing all of these experiments if the amount of error is already acceptable? And really the issue is about how we can actually interpret the results from the point of view of machine learning. Can we actually learn something about the process that will allow us to be more productive? We are going to describe a bit of the model inputs. We have these design parameters. They are going to be labeled as design parameter. This is product characteristics that are describing individual products. It is not categorical. It's information that is extracted from different designs in order to get the proper parameter. Metrology is going to be indicated as process I target J, and it's a label that indicates a measurement J made in process step I. So this is the type of label that we are going to see in the rest of the results. We are also going to have, from the point of view of hardware, what is either a tool state, a process parameter, or a tool ID. So these are the different classes of parameters that we are going to be able to see. By virtue of cross metrology, the targets are represented as process I target J. So this is important to keep in mind when we take a look at the different results. Let's take a look at the first example, when the target is for our first process, the first target that we were selecting. And again, this is a case in which basically we get the results that are similar in both cases. In both cases, for intra-VCM and inter-VCM, we can actually see that the relative order of the importance of these different parameters is very similar between the two. We have a wafer spatial signature 1, tool state parameter 1, design parameter 2, wafer spatial signature 2. So there are slight difference between the two models, but the relative organization of the data and the importance of those parameters is similar between the two approaches. And again, this was something to be expected because, as we said before, in this particular case for process 1 and target 1, there is no prior information. So in both cases, it's exactly the same thing. So even though all of these models were calibrated with slightly different data sets and approaches and random seeds, they are basically all converging to a very, very similar answer. So it gives us a high level of confidence that the training process is done properly. Now, let's take a look at process 2, target 5. If you remember, this is the case in which the intra-VCM approach seemed to have a slightly better improvement in accuracy with respect to the inter-VCM approach. However, this is when we start looking at the differences. We take a look at the very first one, which is this wafer spatial signature one. This is something that it's telling us about the wafer fingerprinting that is happening for that particular step. So, but when we take a look at the second step, we see that we have process 1, target 1. What does that mean? It means that there is, from the point of view of inter-VCM, when all of the information has been provided, it's able to recognize that this particular target of a process ago, process 1, we are already here in process 2. So from a previous process, from an I-1 process, it's the one that is dictating a higher contribution to the final result. That's why it's here listed in the second step. Why is this really important? It's really important because in the absence of that particular variable, basically there is no information about how some of the other parameters or other process steps are affecting the current process step. Basically, all of the information is simply considered as tool state parameters and so on. It doesn't really give us a good indication of what is the relative contribution of that particular process to the next process. And what that unfortunately can lead to is that if we're only focusing on accuracy, we will say, well, we are going to take a look at the intra-VCM approach. It basically will make us focus only in this wafer spatial signature, and we will be spending a lot of time trying to improve the variability of our process, when in reality, that time could have been better spent in the previous process that actually has a very, very, very strong signal in this particular target. So in other words, by including that information, the system is basically telling us, spend more time in this previous process step, because with that information here, you already are explaining most of the variability that is going to be in your final result. So is this a fluke? Is this something that is not repeatable? Well, let's take a look at process 3, target 4. This was the case in which even the accuracy seemed to be better for the inter-VCM approach than the intra-VCM approach. Now we are 3 processes deep. So similar approach. In the intra-VCM approach, we are only using the targets for that same process, the metrology from that case, and all of the prior process information. Now, as we can see here in this particular case, again, basically that process 3, target 3, this is one of the other measurements that are taken for that particular process step. It's telling us that, well, actually there is a very, very strong relationship between target 3 and target 4. Because basically what this says is that knowing target 3, we know the relative importance of that particular target into the target 4 that we were trying to model. But when we take a look at the previous steps, which now we are going to have all of the different targets for process 2 and all of the different targets for process 1, now we can actually see that for this particular measurement, for target 4 in process 3, we have a very, very good understanding on what is going to be the final outcome very, very early in the process. Process 1, target 4 already identifies a very, very strong dependency of that parameter onto basically in 2 process steps, what is going to be the final result, the relative importance, followed by process 2, target 4, which is, again, a process that happens before this one, but now it has, again, a very strong sensitivity. And then process 1, target 3. So this is basically telling us that the top 3 contributions, once we are deeper into the process, it actually comes from previous process steps. Why is this relevant? The reason that this is relevant is where we start learning that it is not sufficient just to say, well, we are going to have a good correlation, and a good correlation is going to explain all of the data. The data can actually lie to us in the sense that it can actually use the existing data in order to explain the measurements. But the benefit of being more physical and basically saying, well, but there are certain effects that happened before. Is there a way that we can actually use those explanations in order to further characterize our process? And the answer seems to be yes. This allows us to not spend iterations in trying to solve a problem when in reality, to really solve the root cause of that variability, the time is better spent in previous process steps. So in conclusion and future work, we define this intra-VCM approach as a method in which only measurements of the same process step are combined to reinforce each other. And we defined an inter-VCM approach in which measurements of present and past process steps are incorporated to better characterize the full process sequence. These results suggest that if we just look at model accuracy, it can be misleading, because it can given the large number of degrees of freedom and the tight control of the process parameters, the model may result in overemphasizing the actual behavior of a particular process. However, the inter-VCM approach delivers a physical interpretation and characterization in which prior process steps, when properly characterized, can be the main drivers in making a more accurate prediction that otherwise will be assumed to be random, when in reality they are systematic and predictable. In the future, what we are planning to do is to extend this methodology to other technology nodes and processes, and eventually connect to process monitoring and control systems. We want to acknowledge all our colleagues in the Siemens EDA and Global Foundry groups, as well as the funding provided by the European Union. Thank you very much for your attention.
Good day, everyone. I'm Sajid Mohammed from the innovation team at ITEC. Today's webinar will be on the IMOCO project. IMOCO stands for Intelligent Motion Control under Industry 4.E. The topic we will discuss today is robots and intelligent mechatronics, edge to cloud advancements for resilient manufacturing. First, I would like to introduce my company, ITEC. ITEC was established as part of Philips around 1991. Then we were part of NXP and Nexperia. And in last July 2021, ITEC became an independent entity so as to sell our products to the external markets and explore new opportunities. ITEC delivers the world's most competitive semiconductor assembly equipment and factory automation technologies for high volume, low cost semiconductor manufacturing. For over 30 plus years, we have been supplying equipments internally to NXP and Nexperia, producing over 100 billion products per year with an installed base of over 2,500 systems. The first class of systems in our portfolio are the die bonder and die sorter equipments. So we manufacture machines which operates at speeds up to 72,000 units per hour with an accuracy of plus or minus 5 micron 1 sigma. And we offer the lowest integral cost for assembly solutions. We also offer from last year assembly solutions for the RFID assembly and also mini LED assembly. We also have tester and in-tape inspection equipments. You can see the tester speeds are up to 92,000 units per hour, and our in-tape inspection equipment speeds are up to 140,000 units per hour. We also offer smart manufacturing solutions for the factory production line for leading in Industry 4.0 for mass production. We offer functionalities like full die level traceability, big data analytics, and so on. So currently we have over 3,700 of such tools connected, which allows for closed loop factory control. So coming back to the IMOCO project, IMOCO is an Excel joint undertaking project which started in 1st September 2021. So It's not been that long now. And there are around 46 partners from 13 countries collaborating on this project. And if you want to connect with us, please follow us on LinkedIn and Twitter, and you could also visit our website. So IMOCO stands for Intelligent Motion Control under Industry 4.E. And in case you are wondering what is Industry 4.E, so it's a lighthouse initiative concept introduced by Excel JU to signpost specific subjects of common European interest. It pulls together the work that is core to the digitalization of industry. So in IMOCO, we try to harvest the fruits of this digital transformation. Data is all around us and it's really cheap. And the computing power is also increasing rapidly. This brings opportunities for new products and systems that can integrate digital twins, AI methods, servitization, and high-performance embedded solutions. So let's look at why we need this digital transformation, for who this is applicable, and how we are going to achieve this. So market is pushing machine performances to their physical limits. To improve, you have to know more about the system behavior. You want to visualize, understand, and master system dynamics. Digital transformation also starts with generating the right data. And you also need to analyze the data and look for correlations in order to realize less downtime, fewer rejects, higher output, more efficient operation of the machine, etc., etc. And this is applicable for machine builders and product developers who seek for more productivity or throughput, who face fast and accurate positioning challenges, who seek for compensation of disturbance sources, who strive for machine data to information, who strive for a more agile development process, and who desire for customized control and drive hardware, and who desire to grasp the complexity of their applications. And in IMOCO, we achieve this by defining fundamental building blocks, architecture layers, pilots, demos, use cases, and work packages. And we will realize the IMOCO reference framework for building the intelligent motion control systems. This block diagram shows how we represent the IMOCO system, environment, and its interactions. So you can see a system represented using sensors, application software, actuators, and the platform hardware, for example, using multiprocessors, FPGAs, and so on, and also system hardware like the stage, robots, fluid system, etc. A system can have inputs and produce outputs, for example, in the production line, and it interacts with the system environment and also with the human user. This diagram shows the architecture view of our envisioned IMOCO reference framework. So this is the initial version of it. You can see 4 layers, or the architecture layers, starting from the sensor and actuator layer, which is relevant for edge processing, up to the digital twin and AI analytics layer, which is relevant for cloud processing. So it starts from the edge to the cloud, and in the cloud you have like server infrastructure, data storage, and analytics platform, and digital twin platform. You could also see that the platform here has an instance and an aggregation. So an instance here refers to the model, or let's say the implementation for one particular machine. And here you can also see representations for multiple machines. So for example, to represent a production line. So this is the first version of our envisioned reference framework. So this is the life cycle view of the IMOCO reference framework for an AI instance in the platform. You can see like the design phase, a manufacturing phase, and a services phase. And this is for, let's say, an AI instance where you have a physical entity, a data, and an AI platform. So this is just to give a glimpse of how we would go about defining the IMOCO reference framework. We also have 10 building blocks defined, which would help us to realize the IMOCO reference framework. So we have building block 1 on SoC or FPGA platforms, building block 2 on high-speed vision in the loop, building blocks on novel sensors, high-performance servo drives, real-time smart control platform, smart control algorithms for condition monitoring, predictive maintenance, and self-commissioning, AI-based components, cybersecurity tools and trustworthy data management, motion or path planning, collision avoidance, and navigation algorithms. And you can see these are spread through the different architecture layers. And these building blocks would be first validated and then realized or integrated with 5 pilots and 4 demos. So the pilots are, let's say, the industrial use cases, or let's say industrial production lines. For example, pilot 1 would be on 3D printing, pilot 2 on semiconductor production, pilot 3 on high-speed packaging, pilot 4 on healthcare, and pilot 5 on mining or tunneling. And we also have 4 demos on high precision cold forming, smart sensoring, autonomous intralogistic transportation, and also on vision-based AI and AI pick and place robotics. So the building blocks would also be validated on these use cases. So we have 4 use cases: a use case on industrial drive for smart mechatronics applications using a lift, use case on CNC for integrated machine tool and robot control, tactile robot teleoperation, and advanced and intuitive robot control and programming control. So all these pilots, demos, and use cases are, let's say, from the industry side, or let's say have industrial relevance, and the IMOCO building blocks will be validated and integrated with these. This slide shows some benefits of the expected results per case, and here you can see key performance indicators or parameters that we use to evaluate the IMOCO project. And we aim to achieve, for example, 50% testing time reduction by using digital twins for pilot 5, and up to 50% reduction of commissioning service or time of new modules to market. And you could also see other performance indicators here. So what is the big technical picture in the IMOCO project? So in IMOCO, we have 8 work packages defined. Work package 1 and work package 8 are for project management and dissemination, so not so technical. But the other work packages, for example, work package 2 brings the system engineering view. So that's the first step in the IMOCO framework development, and it will define how the building blocks could click. And work packages 3, 4, 5 will bring the contents that are mapped onto reference architecture. And work package 6 will bring the validation results of building blocks. And work package 7 will bring the integration results of building blocks in pilots and demonstrators. So how can you benefit from this IMOCO project? So as I already told you, so the IMOCO project started only in the 1st September 2021. So it's still an ongoing project, but the project is also a successor to a previous Excel project, which is the IMEC project. So this video will give you a hint of what you can expect from the IMOCO project.
Yes, it is possible to simulate system behavior earlier and optimize equipment faster, thanks to the introduction of IMEC. And yes, it's working. With many reliable industry and university partners, we achieve a joint approach in control engineering, where the customer leads the application development. It can solve a great deal of your innovation process and reduce management pressure, risks, time to market, and costs. You can do this with the IMEC building blocks. They're easily adapted to your equipment and used to measure, actuate, communicate, analyze, control, and learn. That enables you to optimize your production equipment. For example, the Vexar holds building block 3 to improve accuracy and a reduction of commissioning and servicing times. And building block 4 brings a novel high-speed vision solution to measure the belt edge. Building blocks 1 and 5 are used in this wafer stage to compose position information from different sensors and respond to these signals within 100 microseconds. To perform control engineering, we developed the IMEC Center, a simulation environment that lets you work with our support team, order building blocks, and access tools to work with a digital twin of your innovation. So design and simulate your virtual system at an early stage. Then integrate IMEC building blocks as part of your own system, alone or with help from us. IMEC works and will keep developing. Boost your competence in building smart systems through IMEC and contact us now. Contact us at info@i-mec.eu.
So in the video, you saw like how building blocks in IMEC project was integrated into actual industrial systems. And SACS, which is shown in this slide, is the final product or the final reference framework that was the outcome of IMEC project. So in the IMOCO project as well, we aim to achieve something similar. So for example, like a library with controllers, a communication framework, an extensive graphical UI, and a parameter management. So a generic framework which can be used for intelligent motion control system development and integration. So it's not just the implementation of the actual system. So the SACS also provides the lifecycle management. So it's both the system implementation plus how to manage the life cycle of those systems. So in conclusion, how can you benefit from the IMOCO project? So in IMOCO, we would provide a reference framework for edge to cloud intelligence. And the intelligent motion control systems will be smarter, faster, resilient, highly accurate, highly reliable, and highly configurable. And thank you for your patient listening.